quadratic fields.
Well, thank you everybody for coming. I know this is the last seminar of the semester for number theory. So the title is two-dimensional Galois representations for imaginary quadratic fields. But the focus of the talk will be more for GSP4, for Siegel modular forms. So let's remind ourselves of the theorem of Galois representations for imaginary quadratic fields. If K is an imaginary quadratic field, and pi is a cuspidal representation of GL2, and I want to assume that it's regular algebraic, by which I mean that if you look at the component at infinity, it's a representation of GL2C, and it has Langland's parameter, which goes from C star to GL2C, given by Z maps to Z to the 1 minus K, Z complex conjugate to the 1 minus K, where K is an integer at least 2. And I would also like to assume that the central character, omega pi, is conjugates of, it's equal to its own conjugate. Then the theorem for the existence of Galois representations is that if you look at S, the set of places V such that either V is the infinite place or KV over QP is ramified, and or either of pi V and pi V C is ramified. Then there exists a continuous Galois representation for every prime L, going from the absolute Galois group of K to GL2 QL bar, and such that if P is not equal to L and P does not belong to S, if you look at the restriction, if V a place of K not in S and V not dividing L, then if you look at the decomposition group KV, this is unramified with correct Frobenius action. And this was done in around 93 by Taylor and Harris-Suter-Taylor for S not as above but of density 0. And for S as above, it follows from an article by Weishauer in 2005 and an article by Berger and Hartzosch in 2006. And then the second theorem about this I'd like to mention is the content of my thesis. And that's if V divides, I'm going to call it P, and V does not belong to S, and you also assume that if P is equal to V is inert, then pi V, which a priori is just an unramified principal series, has distinct Satake parameters. Or if P splits, then I want to look at pi V and pi V complex conjugate. If you look at the four Satake parameters of these two representations, they're all distinct. Distinct. then the conclusion is that if you look at rho pi for the prime number p at GKV, this is crystalline. And I'd like, just for ease of notation later, I'd like to remind ourselves of how the proof goes. So, overview of Theorem 1. And that is, well, you use the accidental isomorphism that GL2 over K, well, if you up to complex conjugation, this is isomorphic to GSO 3(1) over the rationals. So that means that if you take pi on GL2 such that omega pi is equal to omega pi complex conjugate, then you end up with something on GSO 3(1). And you can choose a pi hat on GO 3(1) over the rationals. And the next thing you do is you compute the theta correspondence of pi hat to GSP4 over the rationals. And you observe that for sufficiently many quadratic characters, mu, if you look at pi mu, the theta lift of pi twisted by the character mu is non-zero, and it has the property that pi mu at infinity is a holomorphic limit of discrete series. And then finally, you put pi mu in a family of regular holomorphic Siegel modular forms, and use the fact that associated to these objects, there exist Galois representations to construct the Galois representation to your original pi. That brings me to the second section of my talk, which is Galois representations for GSP4. And the relevant theorem here is the following. Suppose pi is a cuspidal automorphic representation on GSP4 over the rationals, such that pi infinity is a discrete series representation. Then the first one, point 1, is that if pi infinity is holomorphic and L is a prime number, then there exists a continuous Galois representation into GL4 QL bar, such that if S is the prime p such that pi p is ramified, union the infinite place, then for p not in S, rho pi L, when restricted to the decomposition group at p, is unramified with the correct action of Frobenius. So this is due to Weishauer in 05. The second part is due to Urban, again in 05. I think all the articles I'm going to mention today that are from 2005 are from the same asterisk volume. So, and oh yeah, but I mean I'm only going. I only have access to the published dates. Well, and that is if pi p. So if p is not in S, then if you look at the action of the crystalline Frobenius on decris of rho pi p, and rho pi p restricted to GQP is crystalline. Then the characteristic polynomial is what you expect it to be. And the third result, this is due to Klaus Sorensen, and it's from 2008. And it doesn't concern, also again, here you have to assume that pi infinity is holomorphic. If pi is globally generic, then you get that for, and this is true over totally real fields, but I'm only going to state it for Q, that if you look at the Veil-Delin representation associated to the local representation at P, this is the same thing as the reciprocity map of pi p, where, I mean here, rec of pi is equal to the reciprocity map defined by Gan and Takeda of little pi tensor similitude character to the -3/2. It's just a renormalization that's necessary for local global compatibility to hold. And so this is for L not equal to P. And if L is equal to P, then rho pi L restricted to GQP, sorry, rho QP is the Ram. And if pi P is unramified, then also crystalline. So a couple of remarks. Well, first, generic means that there exists a Whittaker model. So in particular, pi globally generic implies pi p is generic for all p, including the infinite place, and the converse is not known. I mean, so I don't know much about this converse term, whether having generic at every local place implies global genericity, but I lifted this statement from an article of Jiang and Sudri from 2 years ago, where they show that globally generic representations appear with multiplicity 1 in the space of automorphic forms. The second comment I'd like to make is that if you look at the infinite representation, holomorphic is not generic. So cases 1 and 2 are disjoint from case 3. And in particular, the first two arguments are proved using the algebraic geometry of Shimura varieties for GSP4. And the last one, Klaus's proof, is transferring using a strong theta lift to GL4 and then using results from Harris and Taylor. And this is the one that we're going to use. And one last comment I'd like to make is that if pi is equal to pi infinity tensor pi finite part is globally generic, that means that the infinite component is generic. It's going to lie in the same L packet as a holomorphic one. And in fact, if I flip from the generic to the holomorphic, I also get an automorphic representation. And this was proved by Weishauer, and it's a trick that's used by recent article of Toby G. and David Garrity for modularity lifting for GSP4. Yes?
I have a question. In part 3, there is also a result about the existence of rho pi, I guess, because you said, I mean, this existing result for rho pi is in part 1, where you are assuming that pi infinity is holomorphic, so it doesn't apply in the globally generic case. But in part 3, you give properties of a rho pi that is not defined. So when is rho pi defined exactly?
Wait, so no, so if it's globally generic, then there's a strong theta lift to GL4, and then you just define rho pi L to be rho of the strong theta lift. And this, yes, that's the definition. All right. So the construction of the Galois representation here is based on algebraic geometry, but Weishauer gave a different proof. And this is from, I mean, it appears on the archive as from 08, but again, I don't know when exactly it was proven. And that is, if pi infinity is holomorphic, discrete series, then it is weakly equivalent to pi tilde on GL4. And by weak equivalence, it means that for almost all places P, if you look at the reciprocity map associated to pi P, and you compose it with the injection of GSP4C into GL4C, you get the reciprocity map for pi P tilde. And then you just define rho pi L to be rho pi tilde L. And this makes sense by the Chebotarev density theorem. I mean, it's enough for you to know that these two are weakly equivalent. That there's a weak functorial lift for this definition to make sense. All right, so this is 3. And that's Galois representations for GSP4 at the bat primes. So suppose pi infinity is a holomorphic limit of discrete series. And what happens with the Galois representation when you restrict to a decomposition group if pi p is ramified? And there are some partial results that are known. One is due to Genestier and Thiluin. And this again is in the asterisk volume. And that says that if you look at the representation and you restrict to inertia, this can be described for the following 3 types of pi p's. If pi p is spherical, for the Siegel or Klingon parahoric, plus one other case. And the Siegel parabolic is this, and the Klingon one is this. And parahoric just means that when you reduce modulo p, you end up in one of these 2 parabolics. So now I'd like to present the implications of some computations I've made in the last couple of months. So I'm going to take a prime number, which is odd, and pi cuspidal automorphic representation of GSP4 over Q. But I'd like to mention that Q can be replaced with totally real field F if there exists a weak lift from GSP4 over F to GL4 over F. So when F is Q, this is the content of Theorem 3 due to Weishauer. But I mean, I don't think it's known for totally real fields.
What's the status of office work now?
I don't know. I mean,
much of this is becoming supposed to be. I think he's doing all classical groups. I mean, if it's generic, you know these things. So he can deal when it's not generic. I mean, he's claiming the complete transfer to GLN.
But last time he talked about it was only the semi-simple versions. You have to work a little more to have centers there.
So,
Yeah,
well, if it works, then this can be translated directly without any effort, because, in effect, because I'm using Klaus Sorensen's theorem, which works for totally real fields. Then I have part one, and that, let me make a brief interlude on representations of GSP4 over p-adic fields. And they were classified in '93 by Sally and Tadic. And there's the supercuspidals, and the non-supercuspidals are either induced from Borel or from from Klingen, or from Siegel. And the typical element here I write by chi1, chi2, chi0, where chi1 is the one here, chi2 is the one here, and chi0 is the similitude character. The typical element here is written like this, where chi is a character on this part, and pi is a supercuspidal on that GL2. And the typical element here is written as pi chi, where pi is a supercuspidal on this GL2, and chi is just the similitude character. And there are, for the Borel, they decompose in 6 different ways. I mean, for GL2, they can decompose, they're either irreducible or decomposes and gives you the Steinberg. For GSP4, there are 6 cases. For the Borel, for the Klingen, there are 3 cases. And for the Siegel, there's 2 cases. And these families, have Roman numeral names given to them by Sally and Tadic. So assume pi p is induced from Borel or Klingen. So basically that it is in one of these 9 classes, with one exception, which is induced from Klingen. In fact, it's of type 7. The following things hold. The first one is that there exists a quadratic character eta such that if you look at the veiled linear representation associated to the restriction to the decomposition group at QP, if you forget about monodromy, then this is the same as the reciprocity for pi p, again forgetting about monodromy, and tensoring by eta. The second one is if pi p is either tempered, well, if it's tempered or generic, then you actually get the monodromy as well. So it's the veiled linear representation is, well, Frobenius semi-simplification is the same as the reciprocity map pi p up to this quadratic twist. The third one is, so a small comment about temperedness and generic. For GSP4, it happens that tempered always implies generic, except for two cases, in which case the L packet contains that non-tempered, tempered non-generic and the tempered generic one. So I mean, this should almost always, tempered almost always implies generic. And the third part is that if pi is unitary, oh, so all of this is for holomorphic. If pi is unitary and pi p is generic, that implies that it's actually tempered. And the fourth part, oh, and by the way, if it were unitary, then it's always an expectation that the local components are tempered. So the fourth one is if pi p is of the form irreducible chi1, chi2, chi0, where this is unramified, this is potentially, I mean, maybe ramified, and this is unramified, then I get local global compatibility without any quadratic twist. Now I'd like to mention a couple of corollaries to part 1 plus Sorensen's theorem. And that's the following. Suppose pi p is generic Iwahori. This implies that if you look at the restriction to the inertia, this is acts unipotently. Up to a quadratic character. And you also get 3 things. The first one is a conjecture due to Skinner-Urban on so it says that pi p is paraspherical if and only if the rank of monodromy is 1. The second one is pi p, so let's see, has a unique line invariant under the Klingenhoric if and only if the rank of n is 2. And finally, pi p is the Steinberg representation on GSP4 tensor some character if and only if the rank of monodromy is 3. So all of these come down to a theorem from Klaus Sorensen's paper, and basically the fact that Iwahori implies that it's in cases 1 through 6. So I don't have any exception, because the only exception I have from 1 to 9 is in induced from Klingen. And finally, case is not covered so far. And that's well, I'm going to start here and continue on the right-hand side. If pi p is supercuspidal, that implies that there exists a tau supercuspidal such that the Galois representation is the reciprocity of a supercuspidal. So in some sense, this says that you can recognize whether the local representation at P was a supercuspidal just by looking at the Galois representation. I mean, you're not going to get some coincidences like supercuspidal having the same Galois representation as principal series. Yes. Then the second exception is the ones which are from for the Siegel. If pi p is induced from Siegel, so it's either class 10 or 11, then there exists tau induced from Siegel such that, I mean, the Wilderlin of the local representation is the reciprocity of tau. So again, it's only types 10 and 11 that are indistinguishable from one another. I mean, you can distinguish it from anything else. And the third one is the exception of type 7. And this is a rather annoying exception, but it's the following. If pi p looks of the form chi, so I remind you that 7 is this form, so I have to give you a supercuspidal on this GL2 and a character on GL1. And since I assume that P is odd, that means that supercuspidals are easy to describe. They're just inductions. So if pi p is of this form, then either the Wilderlin representation of rho pi L restricted to GQP is the reciprocity of pi p twisted by my quadratic character, or if I look at pi prime p is omega chi induction from k to qp of tau. And here I want xi to be a quadratic character that defines the quadratic extension k over p, and I want it to be ramified. I also want chi squared to be xi, omega squared to be 1, and omega is not either 1 or xi. And I want psi over psi complex conjugate is omega chi restricted to k, and tau over tau conjugate is chi restricted to k star. Then I cannot tell the difference between these two. And it could just be that the Wilderlin representation is equal to the reciprocity of pi p prime. But this is a very concrete example because your character has to be quartic, and it's a ramified character, and still it's pretty close. So I think that's all the theorem. So what I'd like to stress is that if you knew that your representation was had the Iwahori level at some prime, then you're in this case. So I mean, I think this is as good as I can hope for with my method. Right, the two comments. One is that I assume that P was an odd prime number. The reason is that I deal with a lot of supercuspidals, and so I mean, that's the situation where supercuspidals are easy to describe. And the origin for this quadratic character is that I use a standard L function, not a spin L function for GSP4, And standard L function has the annoyance that it doesn't depend on the character and the similitude part of GSP4. So the way, so a priori it should just be up to any character, and the way you get it that it's actually a quadratic character is that you compare central characters of two automorphic representations. So now for the proof, and the proof is basically rigidity for GSP4. And what I mean is this. So take pi as in the theorem, then by Weishauer, pi is weakly equivalent to some pi tilde. And there's a strong theta left due to, well, the strong part is due to Gan and Takeda to a globally generic representation. So these are precisely the kinds of things that Claus's paper can, for which Claus's paper gives full local global compatibility. So then the conjecture, the rigidity conjecture, is pi weakly equivalent to pi g implies that for all p, pi p and pi pg are in the same local L packet. And now, of course, if you knew this conjecture on the dot, then you would get full local global compatibility. I mean, the thing is that we show as much of this as we can, and which is enough to get the statements in the theorem.
Why is Sala using a trace? Is he developing a trace formula? How does he prove it?
He uses a topological trace formula, and the way it has been explained to me is that the character identities there are very, very hard. So he only gets that the lift is functorial for the unramified representations. And for the ramified one, he doesn't have anything. I think he has some information if the local representation is a theta lift from GO4. But, I mean, in any case, this is the approach that I chose. And let's recall rigidity for GL2. So you have pi and pi prime, which are weakly equivalent. This implies that pi v is isomorphic to pi v prime for all v. And I think typically this is referred to as strong multiplicity 1, but I don't care about the multiplicity 1 part as, just as abstract representation. So it's more illuminating to refer to it as rigidity. Just as abstract representations, they must be isomorphic. And I think it was first done by Miyake, and then Kasselman gave a proof that we generalized. And there's another proof, but I must apologize, I don't know who the author is. And this uses Rankin-Selberg L functions for GL2 cross GL2. So this is the one that we will describe, and it's the actual content of the theorem isn't important for the proof. So let's look at the global functional equation. And that is that the product over all v of the gamma factors associated to pi 1v when I twist by some character eta is 1, which is also equal to the product over all v of the gamma factor of pi 2v when I twist by eta. And let's assume that pi 1v is isomorphic to pi 2v for v not in S. So now what I do is fix v in S, then for w not in S, cancel the terms from the two sides because they would be equal. For w in S, except for v, make eta v very ramified. And then we have the stability result for the gamma factors, which says that gamma of pi 1v twisted by eta v is equal to gamma of pi 2v twisted by eta v. So no matter what you put here, once you twist by a sufficiently ramified character, you're going to get the same answer. So again, cancel. And finally, deduce that gamma w, sorry, I meant w here. And finally, the only thing that's left after you cancel out is that at pi 1v twisted by any character is equal to pi v of pi 2, sorry, gamma v of pi 2v twisted by any character. And now, if you use a converse theorem, you get that pi 1v is isomorphic to pi 2v. So this converse term is due to Jacquet and Langlands. And in general, for GLN, for the converse theorem, you need something like gamma of pi twisted by sigma isomorphic to gamma pi prime twisted by sigma for all sigma representation of GLR for R between 1 and n over 2 implies that pi is isomorphic to pi prime. This is conjecturally. As a theorem, is that if you check it for R from 1 to n minus 2, then true. So in particular, twists by characters are enough for GL2 and GL3, because 3 minus 2 is 1. For GL3, the result, the converse theorem is due to Jacquet, Piasecki, Shapiro, and Shalaika. I don't know off the top of my head a result for general n. But it's useful to exemplify what goes wrong for GL4. Why twisting by characters is not enough, and you actually need to twist by two-dimensional representations. And if you choose pi 1 and pi 2 supercuspidals, then look at pi 1, pi 2, and so this absolute value to the alpha pi 1 direct sum, absolute value to the minus alpha pi 2. These will be non-isomorphic. If pi 1 and pi 2 are supercuspidals, these will still be supercuspidals, so the L function will be trivial. And the epsilon factors, L is equal to 1, and the epsilon factors are equal in effect, because if you write out the formula for the epsilon factors using Gauss sums, this will contribute something, and this will contribute the inverse of that something, so they will cancel out. So here's these gamma of pi 1 twisted by character is equal to gamma of pi 2 A and B. If I look at A and B twists by character, the gamma function will always be the same. However, all right, this leads me to the theory for GSP4. Suppose want to adapt Castleman's proof to GSP4. Well, the problem is that the L function, the spin L function, is only defined for generic representations. because the classical definition of gamma functions involves the Whittaker functionals. So then this led me to looking for a different type of gamma factor that would allow me to adapt this proof. And there are two alternatives. The first one is due to Piatetsky-Shapiro and Sudri. And this involves generalized Whittaker models. I think they're also called Bessel models for GSP4. And but the problem here is that they're hard to compute. So you get a global functional equation, but they're hard to compute and no stability. In fact, Weisshaar uses this type of an L function, but in order to get this kind of an equation, instead of using a stability result to cancel out everything that he can't get a handle on, he says that, well, these are functions of q to the minus s. So by some transcendence argument, he gets that the L functions are the same. But it messes up the epsilon factor because the constants could float around. And the second one, this is due to Piatetsky-Shapiro and Rallis, and Lapid and Rallis, uses the doubling method. The idea being that if you have a representation on SP4, you put pi on SP4, the contragradient on SP4, and pi times the contragradient on SP8. And then define zeta integrals using pi tensor pi tilde instead of Whittaker models. The advantage of this is that stability is known, and is due to Rallis and Sudri. So that means that in reproducing this argument, we end up saying that this gamma factor is equal to this gamma factor, and then trying to apply a converse theorem. And they're easy to compute. Well, in quotation marks. But there are two problems.
But can I ask my question again?
Yes.
Because I guess I should look at Weishaar's paper. But is he using a trace formula? Is he using the converse theorem? Is he using both?
So, no, he only.
Now you seem to be mixing them up.
Well, this is a converse theorem for the local representations, right? I mean, so there are two ways to move from GSP4 to GL4. I think one is due to Asghari and somebody else, but I don't remember.
I mean, for non-generic global stuff.
Well, no, they only do it for generic, and they use a global converse theorem.
The whole point is your holomorphic stuff is
Yes.
globally non-generic.
That's correct. For for holomorphic, which is discrete series, it's some topological trace formula.
So he uses the trace formula there.
Yes.
Does he have to come back and use the converse theorem at some point?
I mean, I don't think so,
Okay.
because he doesn't have anything that's as precise.
So which part of the argument is he?
I mean, he doesn't say anything about the ramified places.
Okay.
So, I mean,
So he's producing something on GL4.
yes,
He says it's cuspidal.
it is cuspidal, automorphic, and you know that it's weakly equivalent. I mean, it's a weak functorial lift of your original representation on GSP4.
And it's proved by the trace formula.
Yes. So, I mean, here when I mean converse, I mean local converse theorems. All right, so the problems with gamma from the doubling method is, first of all, only works with twists by characters. So, I mean, not that there's no intrinsic reason for that, but it's been developed only for that. So you might run into this, this problem. And in fact, this is the reason I cannot tell apart things which are induced from the Siegel case, because the Siegel case is exactly this, which is the same type of a counterexample I gave for GL4. And the other problem is that it's the standard representation, L function, not the spin representation, L function. So that means that the L from the doubling of pi p should be equal to the L due to Godemont and Jacquet for the lift of pi p to GL5, not to GL4. So that means that we get this quadratic character eta thing. And then, so the rest of the proof is basically looking at gamma of pi p twisted by character eta equal to gamma of pi p from the globally generic one twisted by eta, and a combination of comparing L functions and converse theorems for GL2 and GL3 give information about pi p and pi pg. So in particular, we get that pi p is equal to pi pg up to a quadratic twist in the case when it's Iwahori level. So, for example, pi p induced from Borel implies that pi p is isomorphic, well, and I want generic. Pi pg up to a quadratic twist. Now what happens in, so I mentioned that if you didn't assume that pi p was generic, then you would get it up to semi-simplification. And that should be a vacuous statement because you always expect it to be generic, but or tempered. But the logic being that if pi p was not generic, then it would lie in the same induction as something generic. And the gamma factor would be the same because they lie in the same induction. So you would end up pi p not generic in the same induction as pi p prime generic. And this is isomorphic to pi pg twisted by eta. So since they're in the same induction, up to semi-simplification and a twist by quadratic character, they'll give the same representation. And now I have 5 minutes in which I would like to.
Where have you built in that you don't say Sato's Kurokawa type of?
Oh, right, I forgot to mention that. I assume that.
All right.
Yes, pi not cap. Well, I'm just going to write it here. And that's the last one. Applications to GL2 over K. So I remind you that the Galois representation, when restricted to GKV, is known to be unramified if, well, you want KV over QP to be unramified, and both pi v and pi v complex conjugate unramified. But of course, there should be no reason for the ramification of this Galois representation to have anything to do with the ramification of this representation. And the application, which I don't state as a theorem because I haven't written it up yet, but it should work, is that if pi v is unramified and pi vc is an irreducible principal series, then get rho pi L GKV as it should be. And the other application is that if pi v looks like chi1 times chi2 and pi vc looks like chi1 prime times chi2 prime, where each of these contains one unramified representation at least, so irreducibles principal series, where chi1 and chi1 prime are unramified, then again I get a hold on the Galois representation. And the reason I get this is that when you move over to GSP4, the fact that it's a split prime will tell me that the representation on GSP4 is a principal series with at least one unramified character. And that's exactly the situation where I can get local global compatibility without any quadratic twist. So I also get rho pi L restricted to GKV. Now the way I get rid of the quadratic twist is using precisely this L function as opposed to this one, because I know that they're both, I know it's up to a quadratic twist, and this one gives me enough information to deduce that the quadratic twist is trivial. That's all I wanted to say.